Welcome to Lecture 6.1, Quadratic Forms. Throughout, let X be a finite dimensional inner product space. A linear map M on X is self-adjoint if it is equal to its own adjoint and anti-self-adjoint if it is equal to its negative adjoint. These concepts are also called Hermitian and anti-Hermitian, respectively. Now, I'm assuming that if you're at this lecture, you've watched my previous ones, and so you know about adjoints of linear maps. But if not, let me give a quick review. So if M is a linear map from X to possibly another vector space U, here we will assume that X and U are the same, then the adjoint is a linear map from U back to X, and it has the property that if you take the inner product of MX and U, so this here, notice this is an inner product in the vector space U, then that is equal to the inner product of X with M star U. So notice this is an inner product in X. Now this should remind you of the transpose of a linear map, but there's an important difference. The transpose of the linear map also satisfied mx dot u equals, well, I say dot, but the scalar product of mx and u being equal to the scalar product of x and m prime u, the transpose. Now, this did not depend on an inner product at all. For any linear map, there is a transpose map. This here, M star, the definition is based on the inner product structure that we put on X and in U. So changing the inner product structure will change the adjoint. That said, these things are intimately related, and I discussed that in my previous lecture on adjoints. Finally, there's one more important thing that I want to mention, is that if X is over R, in other words, a real vector space, then M star is just the transpose of M. And if X is over C, in other words, a complex vector space, then M star is the conjugate transpose. So over R, the conjugate transpose is the transpose because the complex conjugate of a real number is itself. So this isn't anything different than this. This is just a generalization or an extension of this. So a matrix that is self-adjoint, when it's over R, M star equals M means symmetric. And over C, that means it's Hermitian. In other words, M star equals M bar. And then anti-self-adjoint, when it's over a real vector space, means skew symmetric. So that means that Aij equals negative Aij. And over the complex numbers, it means sometimes it's called skew Hermitian. And that means that Aij equals negative Aij bar. Every linear map M can be decomposed into the sum of a self-adjoint map and an anti-self-adjoint map. And I will write that as M equals H plus A. So H for Hermitian and A for anti-Hermitian. Specifically, A is M plus M star over 2. Notice by construction, this is self-adjoint. So if you take H star, you get M star plus M double star over 2. And since the adjoint of the adjoint is M itself, H star is clearly equal to H. And the anti-self-adjoint part is M minus M star over 2. Notice that if you take the adjoint of this, you get negative A. Let's compare and contrast this to two related constructions. First of all, every matrix can be written as a sum of a symmetric and a skew-symmetric matrix. So we can write M as M plus M transpose over 2 plus M minus M transpose over 2. Now, if we are over a real vector space, this is exactly this construction, but it still works over a complex vector space. It's just not a decomposition into a self-adjoint and an anti-self-adjoint part. Now, let's do a specific example of this for a 3x3 matrix. In that case, the space of linear maps from, say, HOM of R3 to R3 has dimension 9. And let's think about the subspace of symmetric matrices and skew-symmetric matrices. I claim that this has dimension 6 and this has dimension 3. And to see why, let's think about how many degrees of freedom we have when constructing a 3x3 symmetric matrix. I know I've done things like this in previous lectures before. So the 1-1 entry can be anything we want. The 1-2 entry B, the 1-3 entry C, those can be anything we want, but that forces the 2-1 entry to be and the 3-1 entry to be B and C respectively. Similarly, the 2-2 entry can be anything we want. The 2-3 entry we can also be anything. Let's call it F, but that forces the 3-2 entry to also be F. And then the 3-3 entry can also be anything we want. So notice we have 3 degrees of freedom. And so we have a 6-dimensional subspace. Now for a skew-symmetric matrix, well, that means that Aij equals equals negative Aj. So that means that clearly the diagonal entries have to be 0 because Aii equals negative Aii. So these have to be 0. And then if we fix the off-diagonal entries, that will, so let's say that, let's call this one D, that the 2-1 entry, that means that the 1-2 entry has to be negative D. If the 3-1 entry is G, then the 1-3 entry is negative G. And if 3-2 entry is H, then the 1-3 entry is negative H. So here are our 3 degrees of freedom. So this is a 6 and a 3-dimensional subspace of a 9-dimensional space. It's easy to see that these intersect trivially. The only matrix that is symmetric and skew-symmetric is the 0 matrix. And so these are complementary subspaces. So this thing here is equal to the space of symmetric matrices, 3×3 matrices, and this skew-symmetric matrices that are 3×3. Next, every real valued function can be written as a sum of an even and an odd function. Now, I know I talked about this in a previous lecture when I brought up Fourier series. A quick review as to what even and odd means. So an even function means that f of x equals f of negative x. So it means it's symmetric about the y-axis, like any. So x to the 2n will be. And an odd function means it's symmetric about the origin. So it looks like this. So that means f of x equals f of negative x. So if we compare x and negative x, in the first case, they have the same outputs. And in the second case, x and negative x, they have the same outputs, but the sign is different. So any x to the 2n plus 1 is going to be odd. Now, given a function, a real valued function, does not have to be continuous, differentiable, even piecewise continuous, or anything. Just any function that's defined on the real line, we can write it as f of x plus f of negative x over 2 plus f of x minus f of negative x over 2. And it's clear that we have equality here. And it's also clear that this is even and that this is odd. Just a quick recap. A real valued matrix is self-adjoint if it's symmetric. And a complex valued matrix is self-adjoint if it is Hermitian. A key idea of why we care about these things, which I'm not going to prove in this lecture, but I will state because it's important for context, is that if we have a self-adjoint map, then all of the eigenvalues of A are real, and the space X has an orthonormal basis of eigenvectors of A. So we'll actually prove this by showing that there are no generalized eigenvectors, and also eigenvalues for distinct eigenvectors are orthogonal. So if we have multiplicity, maybe we have a two-dimensional eigenspace, so we can certainly come up with, if this is an eigenspace, say for lambda equals 4, in other words, it blows everything up by a factor of 4, we can certainly find eigenvectors that are not orthogonal, but we can also find eigenvectors using like the Gram-Schmidt process that are orthogonal, and we can normalize them to make them orthonormal. This is especially important in spaces of functions, because a lot of times we will have differential operators that are self-adjoint, and when we do, they guarantee an orthogonal basis of eigenfunctions. So I've previously given you a glimpse into Sturm-Liouville theory and Chebyshev polynomials and Legendre polynomials and sines and cosines and Fourier series. All of these things all of those were orthogonal functions. We've seen those, but the reason why they actually arise, why they're orthogonal, is because in all of the cases there was an underlying differential operator that was self-adjoint, and those functions were the eigenfunctions of that operator. When we have an orthonormal or orthogonal basis of eigenfunctions, we can write an arbitrary function using that basis, and we have formulas for what those, so we have f of x equals cn fn of x, something like this. Maybe this is n equals 1 to infinity, and we have formulas. Cn is the projection of f onto fn, and if we don't normalize it, because often it's inconvenient to do so, we have to divide by the inner product of fn with itself. So this is what's called a generalized Fourier series. So Fourier series are the special case of sines and cosines, but we can also write functions in terms of Chebyshev polynomials or Legendre polynomials or many other examples. And I think at some point in this series of lectures I will give you I'll revisit the Sturm-Liouville theory that we saw and talk about how self-adjoint maps and orthogonality arise. Another source of self-adjoint maps are quadratic forms, and we will see these in this lecture. They arise in calculus, in statistics, and many other branches of higher mathematics. We will begin by motivating them by revisiting the second derivative test from calculus. A common problem in Calculus 1 is to use the tangent line to approximate a function f of x near a point. In Calculus 2, one learns about Taylor series and higher order approximations. For example, consider the function f of x, which we know is, here's the Taylor series, 1 plus x squared over 2 factorial, and so forth. If you were to use the tangent line to approximate this function, so of course e to the x looks like this, at say 0, then this line, maybe I haven't drawn it exactly to the scale, so this line is 1 plus x. You are literally taking the Taylor series and truncating it after the degree 1 term. If you were to take a 0th order approximation, then that would just be taking 1 and approximating that with a constant. Now, a second order approximation is if you take the first 3 terms. So that is the best fit parabola to this function, f of x equals e to the x. And similarly, you could take the first 4 terms, the first 5 terms, and so forth. In any Taylor series, the 0th order term is just f of a. So in this case, that's e to the 0. The first order term is f prime of a. The second order term is 1/2 f double prime of a, and so forth. Now, in general, f of x equals n equals 1 up to infinity of f to the nth derivative of a over n factorial times x minus a to the n. And I'm ignoring things like radius of convergence. Sometimes this Taylor series doesn't converge everywhere. That's not important for this purpose. What I'm really focused on is how a second order approximation is an improvement on a linear approximation, which is so popular, so common in calculus. And if you have a critical point, for example, if f prime of a is equal to 0, then the behavior of f, whether it's convex or concave, is governed by this second order term. In other words, it's governed by the derivative, the second derivative of f. All of this extends to the multivariate setting. Now, throughout, I will be a little bit sloppy regarding things like convergence and the radius of convergence, because I just want to give the big picture and how quadratic forms and self-adjoint mappings fit in. So suppose that f is a n variable function. Let's just assume that all of the partial derivatives exist. So I'll say it's smooth. So it is a map from Rn to R. Then if we are near a point A, in this case it's a vector, f of x has a Taylor expansion. And this can be written in terms of all the derivatives. And don't worry about this formula. Just know that f can be written as this infinite sum, where this constant term is the 0th order term. L of x is the first order or linear term. Q of x, or 1/2 q of x, is the second order term, and so on. So now a 0th order approximation is just the constant. A first order approximation is what you get by taking the first two terms, in other words, truncating it after this. And a second order approximation is what you get by taking these first three terms. The 0th order term is f of a constant. The first order term, this linear function here, we know is the inner product of the input y with some fixed vector g. And from vector calculus, you know that that vector g is the gradient of f evaluated at this point A. So it's just the vector that points in the direction that f is increasing the fastest. And this second order term, you also learn in vector calculus, probably not really from this perspective, is the double sum of hij times yi times yj. Now, it's not clear what this is, and I should say why I switched from using x to using y, because I don't want to mix up the coordinates of my input with the actual variables, x1 up to xn, that I'm taking the derivative with respect to. Okay, so what is this? Well, H is this matrix of second partial derivatives. Does this ring a bell now? It's called a Hessian matrix. It is a symmetric matrix because the order that you take the partial derivatives does not matter. Remember that f x I xj equals f xj xi. And now this function, q of y, can be written concisely as y transpose times the Hessian h times y. Or alternatively, as the dot product of y and hy. Earlier in this class, we talked about scalar product notation, and then we generalized that from a symmetric bilinear form to multilinear forms, like trilinear and so forth. You can think of this type of function as a different way to extend a scalar product, from something that's linear to something that's quadratic. And this is called a quadratic form. So think of this as one step up from a bilinear form or scalar product is just degree 1 function, this is a degree 2 function. Indeed, if A is a critical point, in other words, the gradient of f is 0, so think like the tangent plane is flat, then the behavior of f, in other words, whether it's a local minimum, a local maximum, or a saddle point, or something else, is governed by this quadratic function, this quadratic form. Now, it's not an if and only if, because remember, the second derivative test can be inconclusive. You could have a function in a single variable case, like f of x equals x to the 5, or let's say x to the 50, just to make things really extreme, that's so flat near the origin that there's just no way that the second derivative can detect that. You have to go up to the 50 or the 51st order term to actually notice that this is not the 0 function. And that brings us to the definition of a quadratic form. It is a function from a vector space to the field it is over of the form q of x equals the inner product of x with hx for some self-adjoint linear map H. Now let's consider a quadratic form. Q of x, I will write this as x transpose hx, so it looks like this. And in inner product notation, it's the inner product of x with hx. Though we haven't proven it, I'll do it soon. I've stated that if we have a self-adjoint linear map H, then x has a basis, an orthonormal basis of eigenvectors. In other words, H is diagonalizable by an orthogonal matrix P. So here, P consists of the columns of P are the eigenvectors, and P transpose P is the identity because the columns are orthonormal. In other words, P inverse equals P transpose. So normally we write H as P d P inverse, but now we're going to write it as P d P transpose. And what I'm going to do next is take this and substitute it in for H. So Q of x is the inner product of x with hx, or x transpose hx, or x transpose times p d p transpose x. My next step is to look at this p transpose x, and I want to call this z. So p is this rigid motion, it's an isometry, and it sends, so remember that little picture, I'm going to do this more in the next slide. If we have h down here and we change a basis, so I'm doing Rn, but this holds more generally. So our change of basis matrix P goes from Rn to Rn, and upstairs we have a basis of eigenvectors, and D is the matrix with respect to that basis, and downstairs is H. So what P transpose X is, it's like taking your input in here and applying P inverse. So moving that upstairs here to our eigenvector basis. So if we make this change of variables by letting Z be equal to P transpose X, then this quadratic form in terms of Z is Z transpose DZ. So you can see that this is Z, and Z transpose is X transpose P. So this looks like Z transpose times a diagonal matrix times Z, and since the off-diagonal entries are all zeros, this is just the linear combination of lambda I times Zi squared. In other words, lambda 1 Z1 squared plus lambda 2 Z2 squared plus lambda n Zn squared. And I want you to compare how much easier that is than what we had up here, where this was equal to the double sum from I equals 1 up to n and j equals 1 up to n of hij times xi xj. So the big idea here is because h is self-adjoint, we can diagonalize it, and this quadratic form with respect to a basis of eigenvectors has only n terms instead of n squared terms. And it's also much easier to understand this geometrically than up here. And that's what we will finish this lecture with, an example. Here is a quadratic form, q of x equaling x transpose times this matrix, 5, -3, -3, 5 times x. Multiplying this out, it's 5x1 squared minus 6x1 x2 plus 5x2 squared. See where the -6 comes from? That's the sum of these two things. It is easy to check that the eigenvalues of A are 2 and 8. And the corresponding eigenvectors lie on the lines y equals x and y equals -x. So they're like, let me call this z1 and z2. And if these are normalized, here they are right here. So these are orthogonal and they're unit vectors. So this is an orthogonal matrix because the columns are orthonormal. And that means that P transpose P is the identity. In other words, P inverse equals P transpose. And that's why A is diagonalized instead of P D P inverse. It's P D P transpose because P transpose is P inverse. So P, this matrix right here, is a rotation matrix. It's got determinant 1. So if you write this as cosine theta, negative sine of theta, sine of theta, and cosine of theta, then theta equals 45 degrees. So P is a rigid motion that rotates the xy plane 45 degrees counterclockwise. Now the picture that I keep coming back to, that I want you to think of is, so P is the change of basis matrix. So if you have your standard basis down here, and that determines this square grid, in other words, a coordinate system. And it's not clear what A does. It sends these squares to parallelograms, but it's easier to visualize that if you change basis, so P is your change of basis matrix, and that sends, so this is E1 and E2, and this is now Z1 and Z2. Well, these are supposed to be the same length as that. I know I didn't draw it exactly perfectly, but so this grid is rotated by 45 degrees, and now when you apply D, it's easy to see D stretches Z1 by 2 and stretches Z2 by 8. So it sends Z1 to stretch that by 2, and this, I may under-exaggerate this. So it sends this grid, I mean, I should say that the same grid is there, but what it does is so, I mean, the grid is a coordinate system, but it stretches out this direction by 2 and this direction by 8. And then, of course, P sends this back down to here. Okay, so I'm going to continue with this diagram later when we analyze this quadratic form. So moving on, I will let Z be equal to P transpose X as before, or X equals P times Z. In this new coordinate system, this quadratic form, Q of X, is equal to Q of PZ, because that's what X is. And if I plug PZ, this thing, in for X right here, I get P inner product of PZ and A PZ. And that is just PZ transpose times A PZ. And of course, the transpose of PZ is Z transpose P transpose. And so notice that this middle part here is equal to D. That's why I also wrote it in this form. And so this is just Z transpose D Z. Or in matrix form, here's Z transpose, here's the matrix D, and here's Z. And if you multiply that out, it's clearly 8Z1 squared plus 2Z2 squared. So this is easier to understand than this one because it doesn't have this cross term, this x1, x2. Now the graph of this is some sort of surface. I think it's an ellipsoid. That's not clear at all. So what I'm going to do is I'm going to analyze a particular level set of this. I'm going to sketch the graph of this function, which I claim is an ellipse. That's not obvious, but it's going to be easier if we view it in this z-coordinate system. In other words, our eigenvector coordinates. And to see how this works, let's start with a simple example. Let's first plot f of x. Let's do x and y equals 2x squared plus 8y squared. Let's think about what that looks like. And I'm going to say if this is E1 and this is E2, then the unit circle, so this here is x squared plus y squared equals 1. Now let's compare that to, so here's E1 and E2 again. Let's compare that to 2x squared plus 8y squared equals 1. That ends up being an ellipse, and it's going to look sort of like this. I think this is around 0.7, and this thing here is a little bit under 0.4. So it's an ellipse, it's oval shaped like this. So compare and contrast these two things, and now let's go down to try to understand this. So I'm going to start, or I'm going to draw the same commutative diagram, although it's not exactly the same because we don't have a linear function here like we did say up here and with our standard change of basis commutative diagram that we've used in the past. But what I will do is I will draw my basis. I'm going to sort of mimic this diagram, but in both coordinate systems. So this is going to be E1, say that this is E2, and that defines, so let me sketch this coordinate system, this grid. Then up here I'm going to have, this is Z1, and this is Z2. And I'm going to sketch this coordinate system, or this grid. Okay, so let me once again sketch the graph x1 squared plus x2 squared equals 1. That's a circle. And up here, if I sketch, not good at this, obviously, z1 squared plus z2 squared equals 1. That's a circle. So P is, you can think of P as the change of coordinate matrix. So all it does is it changes the grid from here to here. Now let's see what happens when you apply F. So I mean this loosely speaking. Let's draw that same grid over here. So here's Z1 and here's Z2. So here's that, and let me draw this below as well. So this is E1 and this is E2. Now P doesn't actually change the graph, it just changes the coordinate system. So if I were to say sketch this thing down here, it's not clear that whether it's an ellipse or hyperbola or something else or how it's going to be oriented. But if I sketch it up here, now you can see, oh yeah, this is what happens. It's an ellipse and it's longer in the E1 direction than the E2 direction. So of course up here that's the Z1 and the Z2 direction. So if I sketch that, it's going to look sort of like this. And now P is the change of basis matrix. So down here, in this coordinate system, this is just 5x1 squared minus 6x1 x2 plus 5x2 squared equals 1. So in other words, this, I really shouldn't be labeling this with F because this conic section, this ellipse, we can, the best way to construct that is to change to your eigenvector basis, and now you have this ellipse. It's easy to see that that's just how that compresses each in the major and the minor axis, and then go back to your regular coordinate system, and that was this ellipse to begin with. So this is an example of a conic section, which this is an ellipse. Turns out because both of these eigenvalues are positive, if one of the eigenvalues is negative, you have a hyperbola. So I will put a problem like that on your homework. Okay, so moving on, what we're going to do next is look at the eigenvalues and eigenvectors of self-adjoint matrices, or self-adjoint linear maps. I have told you and assumed that they have real eigenvalues and the eigenvectors are orthogonal, but that's something that we probably should prove right away before we assume too much of it. I think I got away with assuming it in this lecture, mostly because I am motivating the idea of self-adjoint maps, and I'm doing that with quadratic forms. So this example was more of a bunch of, or this lecture was more of a bunch of examples, but going forward, we're going to state and prove some of the big ideas and theorems about self-adjoint maps. So stay with us.